Okay, everyone. So I'm going to get into Unit 4 today, and I know there's been quite a significant amount lately. I give you the lab, and you've got the test to finish as well. But I do want to get through it. So just as a general plan, we're going to get through Unit 4 for sure, chapters 8, 9, and 10, and then the plan is I'm still going to put some lessons up as a group for Unit 5, the gas laws, just so you guys have all the material. Unit 5 will not be part of your final mark in this class because it'll be but I do plan on putting videos up and notes for all of it. So you do have that to go over. You can still send me questions, whatever, towards the end of June if you have questions about any of those things going forward towards the grade 12 class. Okay, so I want to make sure everyone gets through all of it. The intro part of Unit 4 in Chapter 8, we're going to start dealing with solutions and solubility. So the first section is about just water and its importance. So if you look at that particular one, I put the note up, it's summarized. It's all really the functions and the things water does and why water is so important. Some of the things we're going to need to remember about water as we keep going is remember water is highly polar. It's a bent molecule, which means essentially you've got your oxygen, and we've got two bonds, two hydrogens. So what you have is not only difference in electronegativity between oxygen and hydrogen means polar bonds, but you've also got a polar molecule with the two ends because of the structure. So don't forget that going forward. So 8.1 you can just read over, not a big deal. 8.2 is not overly difficult, but it's got a lot of important terms in it. So I'm going to go over some of those with you, and you probably heard some before, but maybe don't remember. So it's really talking about what solutions are, right? So a solution is what we call a homogeneous mixture. Right? Remember, if you didn't get this in grade 9 or 10, homogeneous mixtures is two or more substances, but you only see one, there's only one phase, right? The components are universally mixed, which means it looks like one thing. So a great example, and we've probably all made this before, is, or at least I used to when I was a kid, is you take Kool-Aid powder, pour it into water, stir it up, and it looks like you've got just a colored liquid. Okay, that solid powder is gone. It's not actually gone, it's dissolved in the water, and that's what makes it homogeneous. That means that there's two states or two phases, the solid and the liquid, which are now only showing one, just a liquid. Same thing if you like apple juice. When you pour a bottle of apple juice, in the first glass you pour and the last glass you pour tastes exactly the same. That's because it's uniform. Okay, the whole thing is the same. So something that we might not know is that solutions can be any of the three states of matter, right? Air is a solution. Air looks like it's all one thing, but we know that it's composed of nitrogen and oxygen, and it's got some other gases, carbon dioxide, and some other gases in there as well, but it's all mixed and we only see it as one thing. And then solids, we can have them. The best example of solids, and they're special when we call a solution a solid of two solids, is called an alloy when we're dealing with metals. And gold is a great example. 24 karat gold is pure gold. But 10 karat gold means that there's only a portion of that is actual gold, and it's mixed with copper or some other cheaper metals to make. That's why 10 karat is so much cheaper than 24 karat. Okay, now one thing we know is that liquids or gases, they are transparent. Okay, our solutions are transparent because they let light pass through it. Okay, the entities inside are too small to block that light, so they pass through. Solids, a little different story. They can be colored, but they don't have to be. Either one. So there's a diagram that I put in the notes on glucose solution, which is essentially just if you take sugar, a teaspoon of sugar, and put in a glass of water and stir it up, it dissolves completely and you don't see the sugar anymore. We know it's there because if we taste it, we can taste the sugar. Now the opposite of a homogeneous mixture or a solution is our heterogeneous mixture, where we have two or more phases and we can see both of those phases. So oil and water, great example. You put some oil, mix it with water, eventually they separate. We can see both phases. So that particular one is heterogeneous. Now, one thing there can be some confusing ones. Milk is heterogeneous. There's fat droplets that are suspended. We can't see them with the naked eye, but they're actually in there. So milk would be heterogeneous, not homogeneous. And then all of our liquid and gas heterogeneous mixtures, they're translucent or opaque, one of those two. So if we've got, so milk, there's another perfect example. Even though milk looks like it's a uniform liquid, we can't see through it. Light doesn't pass through it very well. It's translucent, therefore it's heterogeneous. Opaque, same thing. Okay, so we're not worried too much about the heterogeneous components, just for now what the solutions are. So when you have a solution, you put two things together, and let's use that sugar and water. If you take a teaspoon of sugar and put it in a glass of water, you've got a lot more water than you have sugar. So the substance you've got in greater amount, greater quantity, that's called the solvent. And the one you've got in lesser quantity and not as much of is the solute. So the solute and the solvent. Another way to think of it is the solute is always dissolved in the solvent. So if I take that sugar, put it into water, the sugar is the solute, into the glass of water, the solvent. Okay? So with those things is my solutions can change, because if I have 1 spoonful of sugar in that water, and then another one I take 2 spoonfuls of sugar and put it in the same amount of water, it's going to taste sweeter. Because what I've done is I've changed the concentration or the ratio of solute to solvent. Okay, so hopefully those things are pretty straightforward. Hopefully that's a pretty solid example. But the other thing I can do is if I've got a particular substance and it's, say, too sweet or too sour, and I don't want it to be, what do I do a lot of times? I could add some more water to it and dilute it. By diluting it means we are adding more solvent and we're lowering the concentration. Okay, so if you add more solvent, you lower the concentration and you dilute it. If you add more solute, you increase the concentration. Okay, so we talked about the gold, the gold is an alloy. 2 metals that are put together is a solution. Those are pretty rare. The ones we're going to talk about for the most part are called aqueous solutions. And anything that's an aqueous solution means that we have added water as our solvent. Okay, so that little bracketed AQ after any one of the reactants or products in our chemical reactions means that we've got water added to that. So that's why it's an aqueous solution. Okay, so I've given you a little bit of questions on 8.2. We're actually going to do 3 things today because it's kind of introductory. I don't think it's too difficult. And the last thing we're going to talk about is when we put things in water, what happens? So remember, we've got 2 types of compounds. Ionic is one we'll deal with first. So picture that crystal lattice of sodium chloride, right, that's there. And we know that water, we've already said that it's highly polar, which means it's got a positive end and a negative end. So when you put a crystal of sodium chloride into water, the positive end of the water, the hydrogen end, is attracted to those negatively charged chloride ions, and the negative end of the water, the oxygen end, is highly attracted to the positive sodium part of the crystal. So what happens is that water goes in there and attracts them, and most of the time the water wins the battle to hold on. The crystal wants to hold stuff together, but the water is really, really powerful. Its charges, so a lot of time it pulls it away. So when it pulls that, the water pulls away a chloride ion, what happens is then it gets surrounded right away by a bunch of water molecules, and that stabilizes it and creates what we call Cl, which is a chloride ion, and we add that little suffix AQ to it. We call that hydrating an ion. So there's a really good diagram in the notes to take a look at that I think explains it really, really well. So take a look at that particular one. Now, what we're doing when we put this particular sodium chloride or whatever ionic substance into water, and we're pulling the ions away from each other, is called dissociation. I'm going to show you a little example of dissociation right now. So if we look at this example, right, I'm going to dissociate K3PO4, which I'm sure you know and recognize. You had to name it as potassium phosphate. So we got to identify how many ions are in each one. Well, I've got 3 potassiums and I've got 1 PO4. Okay, 3 potassium potentially ions, each positive 1, 1 phosphate ion, negative 3. So here's what I'm going to do. I'm going to take this K3PO4, and I'm going to dissociate it. So I'm going to break it into its individual. Right? This is a solid, and now I'm going to change it. So I'm going to have 3 K plus ions, and there is my suffix. There's my little state of matter indicator, moving from a solid to an aqueous ion. And I'm going to have just one PO4 -3, also AQ. Okay, that's called a dissociation reaction. And the key there is moving from that solid to now aqueous solutions for those ions. Okay, so that's the key step in those particular ones. And that happens with all of our ionics. Doesn't matter what it is, all of our ionics are going to be exactly the same. So that's going to happen regardless of what ionic compound you have. That's what you follow in order to figure out your dissociation reactions. Okay, so our other ones are molecular compounds, a little bit different. Right? Molecular compounds, they are a little more variable. Right? Glucose, which we kind of know is sugar, it dissolves real easily in water. But oil, also molecular, does not. Okay, so the question is, why does that happen? A good example, another one we can think about is most organic compounds are not soluble in water. Ethanol, though, is. So the question is, why would that be? Well, it has to do with the shapes. Both are V-shaped, right? So we've got our water. So remember our water molecule. Draw that one for us. Got a little positive charge. Well, negative charge, right? So this is what we've got here, right? It's that V-shaped or bent molecule. Well, ethanol is the exact same thing. And that ethanol being the same, this is what tells us why it's able to dissolve in water. Because if we look at it, we get, if ethanol is essentially the same, then ethanol is going to have a positive end as well, and a negative end, just like water does. And as those molecules come in contact with one another, the positive end of the ethanol will look to join with the negative end of the water, and vice versa, the negative end of the ethanol with the positive end of the water. So they mix with each other really well, and that allows them to be soluble together. So those, what we look for, and essentially one of the things to look for, is when you've got OH bonds. So water is only made up of 2 bonds. It's made up of 2 OH bonds. So that's 100%. If a molecule's got several OH bonds, most of the time, because of the way water reacts and those OH bonds are highly polar, we're going to be able to get those to dissolve in water, those substances with lots of OH bonds. Okay, now, something like oil, which is a hydrocarbon. Okay, hydrocarbons are a series of carbon-hydrogen bonds. Now, most of those bonds are very nonpolar. Almost completely, they're slightly polar, but almost nonpolar. The electronegativity difference is almost the same. It's very, very small. So they're almost nonpolar. Right now, molecules like hydrocarbons, which contain basically nonpolar bonds, are overall nonpolar. Right? Hydrocarbons are also very symmetrical. It's a carbon backbone surrounded by hydrogens. So symmetrical means we don't have that bend, we don't expose any ends, and therefore hydrocarbons overall as a molecule are nonpolar. They surrounded, and I'll draw just a quick one for you. Our simplest one is like methane. Now, even though we've got slight difference in electronegativity, if we draw methane, which is CH4, even though there's a slight difference in electronegativity, you can see, remember we talked about this, that because this molecule, even though there's polar bonds, the molecule is nonpolar because there's no way to get at that central part, which is the negative charge. We can't get in there. The water positive end can't get in there and get in the bond with, and therefore they don't mix. Okay, so the only thing holding those are those London dispersion forces, which we talked about before. They hold them together in their shape, but they don't really hold them together too strongly amongst them. So take a look at those examples I've listed in the notes for you as well. Now, what we're seeing here is that ionic compounds and polar covalent compounds, those dissolve in polar substances. Because ionic really is the most polar you can be, and then polar covalent they dissolve in polar solvents. So polar with polar. Nonpolar don't dissolve in polar, and nonpolar can dissolve in nonpolar solvents. So if you've got, a hydrocarbon and you try and dissolve it in something like iodine, it will dissolve because iodine, I2, remember, completely nonpolar. So it leads us to this rule in terms of, will this dissolve in this or will that dissolve in that? All you need to remember is like dissolves in like. So if you've got something, if you can identify something that this is polar and this is nonpolar, they will not dissolve in one another. But if they're the same, so polar and polar, nonpolar and nonpolar, like dissolves in like. That's the easiest way to remember it. Okay, and the last little thing I put on there is a little description of surfactants. Just take a look. If you ever wonder how, if you get like a grease stain or an oil stain on a piece of clothing, how we get the detergent and how detergent works to lift that stain off, I've got it listed for you in the note. And I don't want to make the video too long, so take a look at those. If you've got questions, great. I'm going to give you the weekend and probably Monday, and then we'll start doing some calculations. We'll still use our mole calculations, N equals M over M. We'll use that a lot still, but we're going to incorporate the number of moles now in a different calculation with concentration and volume. Formula triangle, just like we've been doing, we're going to keep using those. So take a look at this one. If you've got any questions with the notes that are posted, again, always feel free to shoot me a quick message and I'll clarify whatever it is you need. Okay? Try and get the lab and the test done ASAP. Look this over and then we'll get into next week, 8.3 and 8.4. Okay, take it easy, guys, and let me know if you got questions. Thanks.